Alright, previous video we actually derived the matrices of the F is equals to A over L times U, or just U1, U2, where this is equals to your force, or your force 1 over force, your force 1 and force 2. Alright, and then we say that we're going to concentrate a lot on the EA over L, deriving how to derive the stiffness matrix, because as you go further into more complicated stuff, the stiffness matrix may change. Alright, and therefore for a strong form, this is the stiffness matrix is something like this. For a weak form, this is something like, later on we'll talk about it. But in our case, in this video, we'll talk about strong form. Alright, building on from what we have known. So therefore, let's go. From this picture over here, what can you see? We can see that somewhat the force over here is somewhat larger than the force 2, because you are somewhat pulling in this direction, and the geometry may actually change and somewhat moving in this direction, as you can see. Alright, so therefore, just to show you that. Alright, but however, the internal forces within the system, we're talking about always the internal forces, because for a bar element system, alright, within all this, there are a lot of molecular system. So therefore, within itself, there will have a lot of internal stresses, things like that, because when you want to pull it, internal stresses may occur. Alright, but let's just take note of the force internal, where we take the force internal minus the force internal 1, force 2 minus force 1. Let's just not talk about whether is this larger than this, or is this whether F2 is larger or F1 is larger. Let's just take note of just knowing this thing, that's all. Okay, so from at this particular point, we know that F2 minus F1 is equals to 0 for equilibrium system. Okay, and therefore the stresses of F2, alright, multiplied by A, because we know that F is equals to stress times A, correct? So the stresses plus a little small change of the stresses multiplied by dx times dx. Alright, I think this is pretty familiar to you. And then A plus so small changes of dA across a certain changes of dx multiplied by dx. Alright, so it's just simply telling you that A plus dA, and then this is stress plus d stress. But that's because the small changes of stress will be changed due to the small changes of dx. Alright, and things like that. So in order to make the equation equilibrium, because this is stress, you want this whole thing to be stress also, so you need to multiply by another dx. Okay, hopefully you're clear. So this thing over here, just to say, is simply your F internal 2. This thing over here is simply your F internal 1. Okay, which is this one over here. So far so good. Alright, and I will not go into details of proving that this thing over here is this one. Okay, you're just simply multiplying each of them, things like that. Alright, it's just expanding the stuff. Okay, alright, now since we have a stress A over here and a minus stress A over here, we can cancel them each other. Okay, and then this thing over here has a dx degree that is much smaller, like d sigma times dx, dA times dx. In other words, if you were to cancel all the dx over here, you have d sigma times dA. Okay, so this is a second degree of a small number, so it's like 0.01 times 0.01, you have a very small number. As for here, this is just simply d sigma times A, that's all. So it's like a 0.01 only. So if comparatively this one is much larger than this one, and in such of a case that happens, then we can somewhat ignore this and say that they are ignored. So what you have here is only this thing, which is shown over here. Alright, and then you factorize out your dx over here, then you have this thing over here. Okay, everything is equal to 0, still equilibrium. Alright, and then we focus this one. Alright, we go and bring it over here. So we factorize out the dx. Alright, so if you factorize out the dx, you have somewhat d over dx sigma A plus d over dx sigma A. Alright, because you're just simply factorizing out the d over dx and d over dx over here. Okay, by the end of the day, you will have somewhat like d over dx 2 stress times area. But what we do is to just keep it as stress times area will do. Okay, so I don't know why do we write that, but because this is in terms of some very small sigma and small a, so we can assume that 2 times of it is just the same, so we just write it as d over dx sigma a, that's all. Okay, so this thing over here, or this one, is simply this one, okay, which is equals to 0 lah. Alright, I may be wrong for the understanding, but just to let you know that this is just how we derive. Alright, I may be wrong, but once you derive here, okay, why? Because we take this is because dx cannot be 0, dx is just a small number, so therefore this thing should be 0. Alright, therefore we took out this one, we somehow factorize and derive that this is, well, if this is 0, 0 times dx is equals to 0. So we are still going to focus on this thing and going to bring it down over here. Alright, same thing. Now, and therefore, we know that sigma is equals to E epsilon, your E times your strain. Okay, and then they're just simply rearranging, where you bring A over here, you bring epsilon to the other side. Okay, then your strain itself is du over dx. Alright, there is a small change in your du. Alright, over your dx. That's all. Okay, and therefore if you were to sub in this one over here, you have Ea du dx, and therefore if you were to multiply this d, because this d over dx is always outside, so you just multiply in, you have Ea d2u dx squared, which is, you can rewrite all this form, and this is in fact a strong form. Strong form means that you're going to integrate 2 times in order to get the answer. Alright, so integrate 2 times means that you are somewhat very accurate, however you're very troublesome. It requires a lot of time and effort and things like that, and sometimes the system may be so complicated that you cannot solve it, and therefore strong form is not a good way to approach a question. Alright, so therefore just take note that if you have a second order system, just take it like a log. Alright, you want to find your u, you want to find your displacement, correct? If you want to find your displacement, you need to integrate 2 times, which is a very strong log. Alright, if you're talking about the weak form later on, is in terms of some du dx, or which is just du dx, which is somewhat a weaker form or a weaker log, because when you integrate 1 time, you get the answer already. Alright, so this is just the understanding. So in other words, this Ea d2u dx squared is equals to your force. Alright, so you are given a certain forces, and then you're going to rearrange to solve for your u, and the changes, or you can say the displacement. So therefore, this is another way to re-represent your A over L u, alright, or your KU. Okay, this makes me wonder just now what I said just now. We say that we're gonna elaborate E over L only. So therefore, in fact, we are talking about E over L times U. This whole thing is a strong form. I mean, this whole thing can be re-represented as this one, the strong form. Okay, so you have a certain input forces, then you can calculate your U. Okay, therefore, we're talking about the strong form. We're going to talk about this equation, and this is the continuum mechanics, talking about the system that doesn't have a crack. It's a continuous body, that's all. Alright, this is just a bar, then it's just a continuous bar, that's all. Okay, so just take note that F equals to KU, alright, as this shown over here, can be represented in terms of a strong form, a weak form. Alright, in the previous video we talked about the internal system and things like that. It's just a easy way to represent your F equals to KU. Alright, but because you want things to go into more details, because the areas things may change across certain systems, where when complex system gonna come into play, the easy system that we have derived in the previous video is not enough just yet, and therefore we're gonna use maybe a strong form or weak form. But because strong form is tough, and this is why most often in the finite element we deal in terms of the weak form. Okay, and therefore in the weak form, next video and next series of videos, we will talk about the weak form and how all these things comes about into play. Alright, and I shall see you there.